In 8.1, we're going to learn about how to add and subtract polynomials. Let's look at what are monomials. A monomial can be just a number, such as 10, a variable x, or a product of a number and variables, or variables with whole number exponents. Okay, let's look at what's not a monomial, such as 5 plus x. The reason is because it's a sum, and sums are not a monomial. Another one will be 2 over n. You cannot have a variable in the denominator. And 4 to the a power, you also cannot have a variable in the exponent. And for x to the -1 power, you cannot have a negative exponent. Okay, it must be a whole number exponent, such as 5 here. Okay, in order for a term to be considered a monomial. Okay, now let's look at the degree of the monomial. The degree of the monomial is just the sum of the exponents. But for the number, it's a little special here. We don't look at the exponent of 10, which is 1. We ignore that. We need to consider another variable, such as x to the 0 power multiplied to 10. And in that case, 10 times x to the 0 power is just 10 times 1, which equals 10. We would look at this 0. So the degree of any number will always be 0. Okay, and for the variable, we would just go ahead and look at the exponent. For the degree of x would just be 1. And now if we look at the product of a number and its variables, and here we have a coefficient half. We would treat it the same way as a number. The degree of half would still be just 0. And for a, we look at the exponent, which is 1. And for b squared, we look at 2. And then we add all of these numbers up to get 3. And 3 will be the degree of this entire term. And if you have variables with whole number exponents, then of course the degree of -1.8 is still 0, and the degree of m to the 5th power is 5. We add it together to get a total degree of 5. Okay, let's look at the word polynomial. By definition, a polynomial is a monomial or the sum of monomials, each called a term. So each of these are called terms, which is all the parts of a polynomial. And now let's look at the leading coefficient. The leading coefficient is the coefficient of the first term when a polynomial is written with the exponents in decreasing order from left to right. So 2 would be our leading coefficient. And you see all these exponents are written in decreasing order. Okay, and the degree of the polynomial is the greatest degree of all its terms. So 3 will be the degree of this polynomial. And the constant term is any number standing alone in a polynomial. So in this case, 12 will be your constant term. Let's look at a few more vocab terms. Binomial, bi means 2, so it's a polynomial with 2 terms. Trinomial, tri means 3. So a polynomial with 3 terms. And I already talked about terms, and like terms are just terms with the same variable parts, such as here, 3x squared plus x squared. So the same variable part will be just x squared. Okay, let's look at some guided practice problems. Now this first one here, we are to write the polynomial so that the exponents decrease from left to right. So I'm going to take positive 4y to the 4th power, positive 6y to the 3rd power, negative 2y squared, minus 5. Now to identify the degree of this polynomial, we are to look at the term with the greatest exponent, which is 4y to the 4th power. So 4 would be your degree. And to identify the leading coefficient, we would also look at the first term here with the greatest exponent, and 4 will be your leading coefficient as well. Now here we are to tell whether the expression is a polynomial. If it is a polynomial, find its degree and classify its leading coefficient. Is this a polynomial, the first one? And why? I would say it is. Yes, because we don't have a negative exponent, we don't have a variable in its exponent, and we don't have a variable in its denominator. Now the degree of the first term will be 0 plus 1 plus 3, which equals to 4. The degree of the second one will be 0 plus 4 plus 1, which equals to 5. So the degree would be 5. We want the bigger one, the bigger number. And the leading coefficient will be 4. Because if we were to write this polynomial in decreasing order, we would have to put this term first, and then this one. So 4 is your leading coefficient, LC. And then the second one would also be a polynomial. Our exponents are all whole numbers, and there's no variables in the denominator. And then we will have to look at this term. It has the greatest power, so the degree is 3. And then the leading coefficient would be -1 here. And then if we look at the next example, we have negative exponents. So this is not a polynomial. So we go ahead and skip the degree. There's no degree. And the number 7 is a polynomial. Yes, as indicated before. And what I said before, we could assign an x to the 0 power, which still equals to 1. So this degree is just 0. Guided practice continue. Find the sum or difference. Okay, before we simplify this, we need to notice that we need to distribute the -1 here. So that makes -3c, +5. And now we need to combine like terms. +3c and -3c cancels out each other. +9 plus 5 makes +14. So 6c squared plus 14 would be your simplified expression. And for this example, we also have to distribute the -1 here. So we copy 4d minus 6d cubed plus 3d squared. And then we 9d cubed negative 7d plus 2. And again, combine like terms. So here we have negative 6d cubed with negative 9d cubed, and 4d with negative 7d, and everything else. So we're going to have to order this from the greatest exponent to the least exponent. So we begin with this one. Negative 6 minus 9 makes negative 15 and d cubed, and then plus 3d squared, and then we can take 4 and subtract 7 to get negative 3d, and then we have 2 left over plus 2, and this is simplified. Okay, and for this example, we don't have to distribute. We can go ahead and combine like terms. So we have plus 5rs and negative 9rs, and we have our constant terms, positive 3 and negative 12, and everything else. So we can go ahead and rewrite this 3r squared s minus 8rs squared, and then we could take this 5 minus 9, which makes negative 4rs, and then add the constant terms. Plus 3 minus 12 makes negative 9. In this case, we again need to distribute the -1 here. 5mn plus 3m minus 9n minus 13mn minus 2m. Now let's combine like terms. We have 5mn, negative 13mn, and then we also have plus 3m and minus 2m, and then negative 9n is by itself. So let's go with this first. So 5 minus 13 makes negative 8mn, and then plus 3 minus 2, so that's plus m, and then minus 9n. Now in this problem, we're given a shape and we'll have to find the area of the floor plan. Now let's look at the big rectangle here. We could take 4x and times x, which makes 4x squared. Let's write that down. And then we can look at this part. That's going to be x2 squared, which makes x squared over 4. And then we can look at this little rectangle here. It's 8 times x minus 4. So this makes 8x minus 32. And we can go ahead and combine this. So this could be 16 over 4x squared. And then we have 17 over 4x squared plus 8x minus 32 with all the exponents in decreasing order. Okay, for this word problem, I worked out the work for you because there's a lot of steps, and then just the calculation is really simple though. Okay, then the important thing is just to really understand what the word problem is saying. In 1997, the median sale price for a one-family home in the Northeast was about $187,443. And the median sale price for another family here in the Midwest was about $151,629. And from 1997 through 2003, a period of 6 years, the median sale price for a one-family home in the Northeast increased by about $13,857 per year. And the median sale price for another family in the Midwest increased by about $5,457 per year. And in the first part, it wants us to write two equations that model the median sale prices of both the Northeast and the Midwest as functions of number of years since 1997. So if we look at the Northeast now, we have $187,443. That's the fixed price here, and it's changing at $13,857 per year. So I could times that to t and set up my equation. So this is really what you've learned before, okay? And then the Midwest, the setup would be $151,629 and add it to $5,457 times t. So now we have two functions. And the second question here asks you, how much more did a home in the Northeast cost than a home in the Midwest in 1997 and in 2003? Now we need to calculate two amounts here. So in 1997, the time is 0. So I can take n and subtract m. So in the first part here, I did a lot of work for you. I substituted 0 in for t for both functions. And then I had to distribute the -1. Okay? And then you would end up with 187,443 subtract 151,629, because this gets canceled out and this gets canceled out. And then you would get $35,814 for 1997. And for 2003, the time would be a period of 6 years. Now, I found that this was a little tedious, so I took the function for Northeast and I subtracted the function of Midwest to get 35,814 plus 8,400t. And then I took this difference of n minus m and used it here for a period of 6 years. I plugged in 6 in for t. And then after doing the math, I got an amount of 86,214. And to find the change in sale price from 1997 to 2003 for each area, for Northeast, I had to take the function and substitute 6 in for t, because there's a period of 6 years elapsed. And then I substituted 0 in for t for this part, for 1997. So I can cancel out 13,857 times 0, and after doing the math here, I would get $83,142 for the change in sale price for the Northeast. And for the Midwest, I would do the same thing. Substitute 6 in for T. Okay, and then substitute 0 in for T when you subtract the same equation for the Midwest a second time. And you cancel this part out. And then after doing the calculation here, you would get $32,742. And this concludes the lesson.